The marks on these stones are too consistent. That's the problem. Not too beautiful, not too large, too consistent. A variation of just 4.3% across hundreds of cuts in some of the hardest rock on Earth, made, supposedly, by human hands wielding stone hammers thousands of years ago. That number should not exist. And yet, there it is, sitting in the data, waiting for someone to explain it. Let's start with what we know for certain. The granite quarries of Aswan sit on the southern edge of Egypt, near the first cataract of the Nile. This is not soft limestone, not sand, not the kind of rock you chip away at with a bronze chisel. Aswan granite, the pink feldspar-rich stone pulled from these quarries for thousands of years, sits at a 6 to 7 on the Mohs hardness scale. That's the scale that runs from 1, which is talc, all the way to 10, which is diamond. At 7, Aswan granite is harder than most metals. It's close to the hardness of quartz. It's the kind of material that, even today, requires industrial equipment to cut cleanly. And yet, this is the stone the ancient Egyptians chose for their most sacred projects. Obelisks, sarcophagi, the casing of temples, the inner chambers of pyramids. They didn't just quarry it, they shaped it, polished it, transported it hundreds of miles north, and fitted it together with other blocks into structures that have stood for 4,500 years. That's not in dispute. The question, the one that's been quietly bothering serious researchers for decades, is how. The official answer has been the same for most of the 20th century. Dolerite pounders. Workers with rounded balls of dolerite stone, each one heavy enough to require 2 hands, pounding the granite repeatedly until the surface broke down. Archaeologists found thousands of these tools at Aswan. Over 1,400 were documented in one study alone, cataloged by researchers who published in lithic technology. The evidence of their use is real. This isn't a theory invented out of thin air. Dolerite is harder than granite. It sits around 6.5 to 7 on the Mohs scale, sometimes edging closer to granite's hardness, which is actually one of the problems. But we'll get to that. The standard model also tells us that large teams of workers, some estimates put it around 20,000, rotated through the quarry in shifts to keep work going continuously. 12-hour shifts, months at a time, for some projects, possibly years. On paper, that's a reasonable answer to the scale problem. Enough hands, enough time, anything is possible. But here's where it starts to come apart. In 2023, a team of researchers published a study in the journal Geoarchaeology that did something no one had done properly before. They took a real dolerite pounder and a real block of Aswan granite actually on site near the Unfinished Obelisk, and they measured the quarrying speed with precision using close-range photogrammetry. That technology lets you build a 3-dimensional model of a surface from thousands of photographs, accurate down to fractions of a millimeter. They weren't estimating, they were measuring. The result was a quarrying rate of around 216 cubic centimeters per hour at 85 blows per minute. That is a real number from a real experiment. And the researchers themselves concluded in their own paper that the results speak against the use of dolerite pounders alone and support the likelihood that different methods were involved. Let that land. The scientists running the experiment to validate the standard model ended up questioning the standard model. And that's before you look at what the marks themselves actually say. Here's where it gets uncomfortable. When researchers began systematically analyzing the patterns left on the quarry walls, not just looking at them, but measuring them, cataloging them, running them through high-resolution 3D scanning systems, the picture that emerged didn't match dolerite pounders. Not even close. The marks on the quarry surface don't look like impact points. They look like arcs. Long, curved, continuous lines sweeping across the surface as though something moved through the stone in a single fluid motion. There are no interruptions. No splintered edges where a hammer face hit at a slightly wrong angle. No randomness. The spacing between cuts is remarkably even. The depth is remarkably consistent. These cuts don't look like they were made one blow at a time. They look like something moved. When you pound granite with a stone hammer, the surface fractures. It's called percussion fracture. The crystals inside the rock quartz, feldspar, mica crack in multiple directions from the impact. Under magnification, a surface worked by pounders looks like a small-scale battlefield. Irregular depressions, microfractures radiating outward, rough texture, nothing clean about it. That is what experiment after experiment with dolerite pounders actually produces. The surfaces at Aswan show something different. Under microscopic examination, the cut edges show what materials scientists call a shear pattern. A clean, defined boundary between what was removed and what was left behind. The subsurface shows almost no internal fracturing. The stone wasn't broken, it was separated. And on highly magnified samples, researchers have documented what appear to be tiny spiral patterns, consistent, recurring, oriented in the same direction across multiple samples, the kind of pattern left by a rotating tool. There is also evidence of localized thermal alteration on the cut surfaces. Concentrated heat signatures in small contact areas, not the diffuse heat you'd get from grinding two surfaces together, but precise, point-source thermal marks. And particle analysis of some samples has turned up corundum, a mineral with a hardness of 9 on the Mohs scale, used today as the abrasive in industrial cutting discs. None of that is what dolerite pounding looks like. And now we get to the number. When these quarry surfaces were analyzed, mapping the curves of the cuts, the entry angles, the depth, the spacing, the variation across hundreds of individual marks was found to be in the range of just 4.3%. Let's understand what that actually means. When a skilled craftsman performs the same physical action repeatedly, any physical action natural human variation takes over. The grip shifts slightly. The angle changes. Fatigue alters the force. Even professional woodworkers, even expert stone carvers, show variation in repeated cuts in the range of 12 to 20%. That's not incompetence. That's biology. Your body is not a machine. A variation of 4.3% across hundreds of cuts in material as hard as Aswan granite is not what human hands produce. That number sits in the range of mechanically controlled tooling. Industrial equipment, processes where the cutting path is set, not guided. And here's something that makes this even harder to dismiss. The entry angle of those cuts, the angle at which whatever made them enter the stone, varies by less than 2 degrees across all the samples analyzed. Less than 2 degrees. Across different cuts, in different parts of the quarry, at different depths, made if the standard chronology is correct over periods potentially spanning centuries. Now the textbooks don't offer an explanation for that, because there isn't one. Not within the dolerite pounder model, not within any Bronze Age toolset we have any evidence of. But it gets deeper still. There are narrow shafts cut into sections of the Aswan quarry floor. Some of them are up to 30 or 40 feet deep. In some places, barely wide enough for a person to stand inside, let alone raise their arms. And inside those shafts on the walls, at the bottom, in sections where there would be no physical room to swing a dolerite pounder with any real force, the marks are identical. The same arcs, the same spacing, the same entry angles, the same shear cut profile. Think about what that means. The main theoretical tool for quarrying Aswan granite requires something like 18 to 24 inches of swing to generate enough momentum to fracture stone. In some of these shafts, that clearance doesn't exist, and yet the marks on the walls look exactly like every other cut in the open quarry. Same precision, same pattern, same 4.3%. Whatever made those marks did not need a backswing. Now let's go about 400 miles north. At the edge of the Giza Plateau, within walking distance of the Great Sphinx, sits the Valley Temple of Khafre. It's not as famous as the pyramids, but in some ways it's more disturbing. Built around 2500 BCE during Egypt's 4th dynasty, it is lined with blocks of polished Aswan red granite blocks that, in some cases, are estimated to weigh over 100 tons. They were quarried at Aswan, moved north somehow, and set into place without mortar. Fitted so precisely that today, according to observers who have examined the joints, a piece of paper cannot be inserted between some of the stones. A 100-ton block of granite, fitted to tolerances measured in fractions of a millimeter. When the cut surfaces inside the Valley Temple were compared to the surfaces at Aswan, the variation between cut patterns at the two sites came in at under 5%. Different stones, different locations, same method. Whatever process was used at the quarry was the same process, or functionally the same process used 400 miles away at the finished structure. That's not two artisans independently developing similar techniques. That suggests a standardized, controlled, systematic method of working granite across the entire region. And here's the reversal that makes all of this genuinely difficult to explain away. In every civilization we know of, technology improves over time. Early efforts are crude. Later work is more refined. That's the pattern we see in pottery, in metallurgy, in architecture, in writing systems. Progress moves in one direction. So if ancient Egypt was developing its granite cutting capability over centuries, the oldest marks should be the roughest, and the later marks should be the most precise. Researchers found the opposite. When the cut patterns at Aswan were analyzed against estimated age, comparing older sections to more recent ones, the trend runs backward. The oldest looking marks are the most consistent, the most precise. The later marks degrade. The oldest work, by whatever measure of age can be applied, looks the most mechanically controlled. The newer work looks more like what you'd expect from human hands. That's not the story of a technology being invented and refined. That's the story of a technology being inherited and gradually lost. If that's true, it rewrites the question entirely. The question isn't how did the ancient Egyptians develop these techniques? The question becomes, from whom did they inherit them? And how far back does this actually go? Consider the unfinished obelisk. Still attached to the granite bedrock at Aswan, never removed, never raised, never finished. If it had been completed, it would have stood around 42 meters tall, roughly 137 feet, and weighed somewhere in the range of 1,200 tons. That is not a rounding error. The largest obelisk known to have been successfully erected in ancient Egypt, the Lateran obelisk now in Rome, weighs about 455 tons. The unfinished obelisk would have been nearly 3 times heavier. It would have been the heaviest single stone monument ever raised by any civilization in antiquity. The official explanation for why it was abandoned is that workers discovered a significant crack in the granite partway through. A reasonable explanation on the surface. Cracks happen. You don't waste more effort on a flawed stone. But when researchers looked carefully at the obelisk, they found something the standard explanation doesn't quite fit. There are cut marks continuing beyond the crack location. Work appears to have continued after the crack was already visible. If the crack was the only reason for abandonment, the work should have stopped at the crack. It didn't. And more than that, the cut marks on the unfinished obelisk are identical to the cut marks on every other surface in the quarry. Even in the lower sections of the trench, where clearance is extremely limited, the precision doesn't change. The consistency doesn't drop. Whatever was cutting this stone wasn't affected by the spatial constraints of the trench. 1,200-ton obelisk, abandoned mid-project, with cuts that match industrial tolerances in spaces too tight for a human worker to swing a tool. What stopped them? That question has never had a satisfying answer. Now, lay the data points side by side. 1. Aswan granite sits at 6 to 7 on the Mohs hardness scale, harder than metal, requiring serious industrial effort to cut cleanly even with modern equipment. 2. A 2023 published experiment at the unfinished obelisk site found that dolerite pounders alone produce results inconsistent with the scale of the work, and the researchers themselves concluded other methods must have been involved. 3. The cut surfaces show shear patterns and spiral micro marks consistent with rotary tooling, not percussion fracture consistent with hammer blows. 4. Corundum particles, hardness 9, used in modern abrasive cutting have been recovered from surface analyses. 5. The variation across hundreds of individual cuts is in the range of 4.3%, which sits inside the tolerance range for mechanical tooling and well outside the range of human handwork. 6. Entry angles across hundreds of cuts vary by less than 2 degrees. 7. Identical cut patterns appear inside narrow shafts where no hammer swing was physically possible. 8. The same cut signatures appear at Aswan and at Giza, 400 miles apart, with variation of less than 5%. 9. The oldest marks are the most precise. The newer marks degrade. The technology appears to run backward. That is not one anomaly. That is not 2 anomalies. That is a pattern. The pattern doesn't prove what made these marks. That would require something to be found, a tool, a mechanism, a written description, a diagram. None of that has been found. What the pattern does is something arguably more important. It proves that the explanation we've been given is insufficient. The dolerite pounder model is not a lie. The pounders were real. They were used. There are thousands of them at the site. But the evidence, experimental, microscopic, statistical, increasingly points to the conclusion that pounders were not the whole story. Maybe not even the main story. Published researchers have said as much in peer-reviewed work. So what was the rest of the story? Some engineers argue the Egyptians may have used a form of abrasive cutting copper or bronze tubes loaded with sand or harder abrasive material, used as rotary drills, a technique that has been seriously proposed since the work of engineer Christopher Dunn, who spent years analyzing surface marks and drill core samples from Egypt, and argued the precision matched, not hand tools, but mechanically controlled abrasive processes. Whether that fully accounts for what we're seeing at Aswan is still an open question. Others point to the fire-setting evidence, charcoal, ash, and burn material found in the quarries alongside the stone tools, suggesting that heat was used to weaken the granite before cutting, a technique used in European quarrying much later in history. That could explain some of the cut efficiency. It doesn't explain the consistency. What no conventional explanation has managed to address is that single number, 4.3%. Consistent entry angles within 2 degrees. Cut signatures matching modern rotary abrasive processes at a confidence level that, in any other context, would be reported as a significant finding. The microscopic evidence of shear cutting rather than percussion fracture in stone harder than steel. These are not the marks of people who were just very patient with stone hammers. The ancient Egyptians built things that still stand. They quarried stone in quantities that we have trouble matching with modern logistics. They fitted blocks together at tolerances that modern stonemasons regard with something close to envy. All of that is simply documented fact. But the question, and it keeps coming back, no matter how many times the textbooks close the chapter, is whether the tools and techniques we've assigned to them are actually equal to the evidence left in the stone. The stone says something different than the textbooks. It has been saying so for a long time. Here's what you're left with. Either thousands of Bronze Age workers with stone hammers somehow produced surface variations equivalent to industrial machining in stone harder than steel, including inside narrow shafts where a hammer couldn't have been swung, or something else was happening at Aswan. Something that left marks so precise, they've now been flagged by pattern recognition analysis as matching modern industrial processes more closely than any ancient tool on record. We're not going to tell you what that something was. Nobody can, not yet, maybe not ever with what currently survives. But the question of how ancient Egyptians cut granite is no longer a settled question. It's an open one. The experimental evidence opened it back up. The microscopy keeps it open. And that 4.3% number refuses to close it. The stone is still there. The marks are still there. And they're still waiting for an explanation that fits all of them, not just the convenient ones. What's directly beneath the Giza Plateau may hold part of the answer. Researchers have been arguing for decades about what the ground-penetrating radar surveys have turned up under the sand chambers. Tunnels, anomalies, the official excavation record doesn't acknowledge. That's where this goes.